Hello everyone. The research project we're going to discuss is on fault tolerance and resilience in IoT and blockchain networks. Our group consists of three members: myself, Vishwadatta Godapati, Suriteja Merugu, and Niharika Pendem. Coming to the introduction, in today's interconnected world, the fusion of Internet of Things (IoT) and blockchain technologies holds immense promise. Yet it also presents unique challenges. So, our presentation, fault tolerance and resilience in IoT blockchain networks, delves into critical domain of ensuring uninterrupted operations and data integrity in these integrated systems. With the foundation of our research paper, we address the pressing need of fault tolerance and resilience. Well, we'll explore how IoT devices and blockchain infrastructures can withstand device failures, network disruptions, and malicious attacks. By the end of this presentation, you'll gain insights into innovate protocols and strategies designed to bolster the reliability and trustworthiness of IoT blockchain networks, even in adverse conditions. This is the agenda of our research. Coming to the problem statement, we have taken several problem statements here. The first one is integration complexity. The convergence of IoT and blockchain introduces complexities in maintaining a seamless connection between a myriad of IoT devices and decentralized nature of blockchain. The next one was vulnerability to failures. IoT devices are prone to hardware failures, and blockchain networks can face downtime due to various factors, making fault tolerance crucial in these cases. The next was data security. Ensuring data integrity and confidentiality is challenging in IoT blockchain networks, especially when exposed to malicious attacks. The next one was network disruptions. Connectivity issues and network partitions can disrupt data flow and conscience in these integrated systems. Consciousness. A lack of robust protocols. Existing protocols may not effectively address these challenges, leading to potential system vulnerabilities. The research objectives of our project are enhance fault tolerance, which was developing innovative mechanisms to enhance fault tolerance in IoT blockchain networks, reducing downtime and data loss, and also ensure resilience, create strategies for network resilience, and allow continuous operation even during disruption attacks. Protect data integrity, implementing measures to safeguard the integrity and security of data transmitted and stored within the system. Evaluate existing solutions. Assess the limitations of current fault tolerance solutions in IoT blockchain networks. And to propose innovations. Introducing novel consensus mechanisms, redundancy strategies, and adaptive fault recovery techniques. The last one is advanced reliability, aim to advance in reliability and trustworthiness of the integrated IoT blockchain systems. Coming to the methodology, we have taken some steps following the methodology to create the project. The first one was literature review. We conducted an extensive review of existing literature from different papers which are existing on this environment of our project, and on fault tolerance with IoT and blockchain to understand the current state of the field. The second step was data collection. We gathered real-world data related to IoT blockchain network failures and vulnerabilities for analysis. And the third step was stimulation. We utilized stimulation tools to recreate fault scenarios and evaluate the performance of proposed protocols and mechanisms. Experimentation was the next step. Conducted experiments with IoT devices and blockchain nodes to access the practical viability of proposed solutions. The next step was data analysis. We employed data analysis techniques to interrupt stimulations and experimental results, identifying strengths and weaknesses. The last step was iterative development. Iteratively refined protocols and strategies based on the findings to achieve optimal fault tolerance and resilience.
So coming to the IoT blockchain overview, Internet of Things describes the network of physical objects that are embedded with the sensors, software, and other technologies for the purpose of connecting and exchanging data over the internet. Coming to the blockchain technology, it is a distributed ledger technology that combines with IoT to make machine to machine transactions possible. So, the integration between these two is a study in our study. IoT devices generate data that is securely recorded on a blockchain, enhancing data integrity and trustworthiness in IoT applications. So, there are few fault scenarios existing. So, in case of device failure, this can be resulting in the data loss or a communication breakdown. So, in case of a disruption, network disruption, connectivity issues such as the network partitions, congestion, or outages can interrupt data flow between IoT and blockchain. Due to malicious attacks like DDoS, data tampering, or ransomware can compromise data integrity and disrupt the normal flow between the IoT blockchain operations. And the data corruption, coming to it, unintentional data corruption can be caused due to transmission errors or a shortage issues can affect the reliability of recorded data. And coming to smart contract vulnerabilities, in smart contract vulnerabilities, this can be lead to unauthorized access and manipulation of IoT data. And there are few existing solutions for the previously discussed false scenarios. Coming to the consensus algorithm, existing solutions often rely on traditional consensus algorithms like proof of work POW or proof of stake POS to maintain blockchain integrity. So, in redundancy systems, some systems incorporate redundancy through multiple nodes or data replicas to enhance fault tolerance. We'll discuss it in detail in the coming slides. Encryption and authentication. Security measures such as encryption and authentication protocols are used to protect data in transit and at rest. There are few limitations for these existing solutions. This may struggle to handle IoT scale data, and proof of work can be energy intensive. Redundancy increases overhead, and security measures may not fully address emerging threats. So, innovative consensus mechanism. Consensus mechanism is a protocol that brings all nodes of a distributed blockchain network into on a single data agreement. uh, Dynamic consensus that adapts to network conditions. When faults are detected, the consensus protocol can shift to a more fault tolerant mode. Fast block confirmation. We employ a fast block confirmation mechanism to minimize the impact of network disruptions and reduce confirmation time for transactions. Adaptive node participation, in this we nodes in the network can dynamically adjust their participation levels based on their reliability, reducing the impact of unreliable nodes on the overall network. Coming to the decentralized redundancy, what is decentralized redundancy? It is an approach where the data copies are distributed across multiple nodes in a decentralized manner within the blockchain network. So enhancing resilience, the enhancing resilience, data recovery, and load distribution are the advantages for the decentralized redundancy. So enhancing resilience. Decentralized redundancy significantly improves network resilience by ensuring that even if some nodes fail or data is compromised, multiple copies of same data exist on the other nodes. So the decentralized redundancy can enhance resilience. Uh, Coming to the data recovery, as the data is decentralized across multiple nodes over the blockchain, the data recovery can be easily done in case of a failure or a loss of data in any node, because there are data stored in other nodes over the blockchain. So the load distribution redundancy also aids in load distribution, preventing any single node from becoming a bottleneck in the network.
Adaptive fault recovery techniques. Dynamic node replacement. Our technique involves
involves the dynamic replacement of failed nodes with healthy ones, ensuring uninterrupted data processing. Data reconstruction. In the event of data corruption or loss, adaptive techniques facilitates data reconstruction from redundant copies. Fault detection algorithms. Advanced fault detection algorithms continuously monitor the network and trigger recovery process when anomalies or failures are detected. Resilient smart contracts. We develop smart contracts that can automatically execute recovery actions, reduce manual intervention. Coming to the results and findings, enhanced fault tolerance. Our research demonstrated a significant improvement in fault tolerance with the system maintaining operations even during extensive device failures. Uh, Reduced downtime. The adaptive fault recovery techniques reduces downtime by 30% compared to the traditional solutions, ensuring uninterrupted data flow. Data integrity. Findings showed a 98% success rate in data recovery, reinforcing the security and integrity of IoT data. Energy efficiency. Innovative machines reduced energy consumption by 25% compared to POW, addressing sustainable concerns. Coming to the discussions, resilience in critical applications. Our research has a significant implications for critical IoT applications such as healthcare and supply chain management, where uninterrupted operations are paramount. Security and trust. By enhancing fault tolerance and data integrity, our findings contribute to increased security and trust in IoT blockchain networks, making them more appealing for various industries. Sustainability. The energy efficient mechanisms align with sustainable goals, reducing the environment footprints of blockchain networks. Future adoptions. The findings pave the way for wider adoption of IoT blockchain integration, especially in scenarios where data reliability and trust are paramount. Coming to the future work, scalability. Future research can explore methods to further enhance scalability accommodating the growing number of IoT devices and transactions. Privacy solutions. Investigating advanced privacy preserving techniques to protect sensitive IoT data while maintaining transparency in the blockchain networks. Edge computing integration. Explore the integration of edge computing with IoT blockchain, optimizing data processing and reducing latency. Standardization. Work towards industry standard protocols for fault tolerance and resilience in IoT blockchain networks to ensure interoperability. Cross-domain applications. Extend research to diverse domains, including smart cities, agriculture, and logistics, to address the unique challenges in each sector. And coming to the conclusions, enhanced reliability. Our research contributes to the enhanced reliability of IoT blockchain networks by addressing fault tolerance and resilience challenges. Continuous operations, adaptive fault recovery, decentralized redundancy, and innovative mechanisms ensure uninterrupted operations even in the face of distributions or and attacks. Data trustworthiness. To study reinforces the trustworthiness of data generation by the IoT devices and blockchain networks, vital for applications across industries. Sustainability. Energy efficient protocols align with sustainable goals, making IoT blockchain integration environment friendly.